And we're still talking about doing root locus by hand. This is now the third video of that. Still, here was the example. We start with this L of S. We went through this whole example. Remember this L of S for a second. We went through the first four rules. Which got us to here. And we could really stop there for this example. And by the way, my numbering of rules might not be common in all textbooks. I'm not sure. But let me talk about, there's going to be two more rules, rules 5 and 6. And that's what I'll talk about in this video. Rule 5 is, where do the root locus cross the imaginary axis? I'll just say in this example, we could pretty much tell there's nothing attracting poles or branches into the right half plane. So we could tell at this point that we're not going to cross the imaginary axis. But let me just talk about how you would do that. We have to use Ruth-Hurwitz. So it's a little tedious. Remember the closed loop transfer function is this guy. And if you do a little algebra ahead of time, here's the closed loop transfer function. And we're interested in, for root locus, for Ruth-Hurwitz, I should say, we're interested in the denominator there, the characteristic equation. And it's just going to be the denominator of our L plus the numerator, basically. So here's our KL. The characteristic equation is going to be this denominator plus this numerator. Okay? I'm just trying to give you a tip on how to set up that characteristic equation. Simplify that, you get this. And from this, we can do Ruth-Hurwitz. We're going to get you got a 3, s to the 3, so we're going to need 3, 2, 1, 0, 4 rows in the Ruth array. The top row will be 1, 31 plus k, 4k. No, let's see. Yeah, this is all constant. So 1 and then 31 plus k. And the second row will be 7 and 25 plus 4. I'm not going to go through the arithmetic, but here we see, and we're only interested in for k greater than 0. As long as k is greater than 0, you never get a sign change in this column. You don't get any crossings of the imaginary axis. We'll do more examples of this later where you do get crossings. So that's rule 5. To do rule 6, I'll do another example. I'll try to do the early rules quicker. So here's what we'll say our L is. 1, 0, 2 poles. Poles at -1, -3, and a 0 at -4. Here's step 0. We just plotted the poles and zeros of L. Where's the root locus going to be on the real line? Start out here, 0, hit here, you get 1. So it's on the real line to the left of this pole. At this point, it's 2. So nothing here, and then back again here. That's where it's on the real line. Okay? And if you did departure angles, these guys are all on the real axis. I won't go through these calculations because we did that kind of stuff before, but from this pole, it's going to go out of this pole strictly left, out of this pole strictly right, into this 0 from the left. This would be, by the way, an arrival angle of 180 degrees. Think of a little line coming out of that 0 straight left, but the root locus comes in along that line. This was a case of n minus m where it's just 1, so you get a single asymptote straight left. We've got another branch that goes out to the left. What happens after rules 1 to 4? There's nothing attracting it into the right half plane, so I'm going to say rule 5 won't apply here. Now what? You've got a pole coming left here and going right here, and then coming into that zero and off to the left. So it somehow has to get from here over to there. Each of these poles do. And it's got to be symmetric around the real axis. So somewhere it's going to join somewhere along this thing. And one pole will go up, one will go down, and they have to somehow come back to the real line over here. I say think circular-ish. Always a pure circle, but it's a good guideline. And here's where we need rule 6, which says, where does it leave and come into the real line? Break in and break out points. There's a necessary condition for that. The derivative of L with respect to S has to equal 0. So if you think of L as having a numerator B over denominator A, you know, the quotient rule of derivatives, this must be true now. This is just the quotient rule of taking the derivative. So here's our example. The numerator is B, so that's S plus 4. The denominator is this guy. Multiply that out, it's squared plus 4S plus 3. Apply this formula. Let's see. A squared plus 4S plus 3 times the derivative of B, which is just 1, minus B, which is S plus 4. And the derivative of this A, which is going to be 2S plus 4. Simplify that. You get a quadratic. Use the quadratic formula. And it says, there's where you're going to have branches break out or break in to the real line. Minus 4 plus or minus square root of 3, or about minus 2.3 and minus 5.7. Go back. See, 1, 2, 3, 4. So it's going to be centered here. And then add the square root of 3, which what, a little over between 1 and 2. So somewhere around here, it's going to come off. And then it's going to break in somewhere around here. If I say think circular-ish, one branch is going to go up around in a semicircle back in, and we'll go into this 0. Another will break off in the semicircle, break back in, and go left off to minus infinity. Here we go. One moves left, this one moves right, and one goes up, one goes down, break back in at the same point, and one goes right, one goes left. One goes right into this 0, and one goes left along this asymptote to minus infinity. So that is rule 6. Here's the formula sheet for rules 1 through 6. And I let my students have this formula sheet on exams and homework. You might say, MATLAB can do this, so why are we doing it by hand? For one thing, it helps you get an intuitive feel for the relationships. And we're going to use Root Locus to do some design. And there you have to be able to think, what happens when you add a pole or a 0? So you need to kind of get a feel for Root Locus and what more poles and zeros do, and where you might place them to get the design you want, etc. And this is just good old control systems 101 stuff. The tradition. I don't know if you take a course if you'll have to do this or not by hand. If you don't have to, you probably don't want to go through this pain. Rules 5 and 6 don't always have to be applied. They're the more difficult rules. I usually told my students when to apply them. And rule 4, doing it the exact way with taking inverse tangents with a calculator, I also usually told my students when they needed to do that versus just doing it by eyeball. And there's both science and art to this, and you're going to have to do some examples on your own before you start getting the feel. Don't think you can just pick this right up from watching my videos. I'll do some more examples in future videos, but at this point, we've been through all the rules of doing root locus by hand. The other examples are just more examples.